With, I thought I'd quickly go through some of the mid-sem tests. Uh, the mid-sem tests, I don't know if you've checked your marks, they were a bit lower than we've had in the past. Um, with an average of just over 11. So, not ideal. Ideally, sorry? No, we don't scale you. It looks poorly on Andy because he did that half the course earlier. Um, no, yeah, so we won't be scaling it typically because you tend to get higher marks in your labs. Most people are getting through the labs, and we think it's fair enough to even out. Also, the real reason for the mid-semester test is just to give you a kick up the backside, right? And I hope you should all realize this. Frankly, it was quite easy if you actually studied, but there was a lot of notes to cover. I'm not going to go into much detail on a lot of the questions. Starting off, but I will walk through it quickly. So in terms of NEOS instructions, a lot of this you could actually do without having even taken the course, which is another thing to consider. Just take your time when you're working through an exam and read the question and have a good guess. So what happens if you get an OR instruction of a certain value? Well, you can see the biggest question mark is what happens. So we got what do you do with the extra 4 that's undefined? Now, if you know an OR instruction with an EOS, you only define the least significant 6 bits. What happens is the later 16, most significant 16 bits are all considered to be a 0. So, ORing a 0 with anything is just going to be the original value. So you can quickly grab all that and just copy this across. So 55AA. What happens with the second half? Well, if you OR 0FA, so A ORed with A is what? A. A ORed with 5, so what's A? A is 1010, 5 is 0101. F. F ORed with 5, F ORed with anything is F. And 0 ORed with 5 is obviously 5. Easy enough. The AND, again, it's the exact same thing, except it's an AND function instead. So if you AND zeros with values, what do you get? Zeros. So your most significant 6 bits are all going to be 0. Sorry. Then the next set, again, just ANDing. ANDing an A with an A, you get an A. ANDing A with 5, if I AND those together, I get zeros. And an F with a 5, you get 5. F with anything ANDed is itself. And ANDing a 5 with a 0 is obviously a 0. So that should be trivial enough. XOR, you guys can do that, I'm not going to bother. Exactly the same process. Conditions. This stuff you've practiced in the labs and it's all written in the notes. So these should be 3 free marks. Now to give credit to you guys, most people scored reasonably okay on this question. People did terribly on question 2. So what's going on? We got some diagram here, and again, actually you don't need to, you've had it all explained in the course, but you can always just go back to your digital logic and try and solve this question. So, right, you got some memory mass address space, 16-bit bus, and how many of the bus lines must be decoded to generate chip select signal? So, well, what am I trying to do? Chip select signal is here, so I'm enabling that somehow. I know I've got address lines 0 to 15. Let me have a look at this diagram carefully. Well, I've got address lines 0 and 1 there. So an intelligent guess of what's left, 14 is your answer, just by looking, thinking, guessing. Okay, so how do you generate this chip select line? So this is some location in memory which you're going to try and set high. Now obviously you don't care about bit 0 and bit 1 because they're going to actually do something within the chip select. So what do you do with the other 14 bits? Well, you want to create this base address. So you know so basically all this question is asking is how do I generate this function using digital logic? So how do I generate a C with, what is this? This is, ding ding, someone had a good idea. Well, it's just 1 1 1 1 1 1 0 0 0 0 0 0 0 0 0 0. That's expanding FC into binary. Okay. So how do I generate that function with digital logic? Well, what is this? This is A0, this is A15. So I want A0 bar, A1 bar, A2 bar, dot, 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 all the way up to here. Then you have A15, A14, A13, A12, A11, 1, 2, 3, 4, 5, A10. So that's these 6. I've got all my most, and then all the rest are going to be 0, so A9 bar. That's my digital logic function, and I'm almost done. So that's how I generate the address. What else do I have to do? Yeah, you just notice that you've got this bar on CS bar. Stick a big bar over the top of it. You're done. Okay. Again, okay, memory foldover is this idea of how can we basically make a memory a bit easier to save a bit of hardware, is what we're trying to do with memory foldover. So that's when multiple address locations can get the same memory. So if you had, say, 10000000, and yeah, yeah. Sorry, that's true. You don't need those 2 bits. Yeah. So yeah, those are not included in the logic function. Yeah. Yeah. The end. Yeah. Yeah, that's what's the same question. You just don't need those last 2 bits because those last 2 bits are actually just passed straight into the PIO device. So it's the base address, and those least significant bits are offsets from the base, right? So you just don't need them in the function. Memory foldover is the idea, sorry. It's the idea that if you had some function, this was some memory address, and you also had a different set of inputs, and you were writing first to this memory address and then to this memory address, what happens if, well, I ignored the most significant bit, or that was a don't care, in which case both of my writes would be to the same address. So it's just ignoring some most significant bits and allowing you to save decoding hardware to create the most significant bits, which is the answer to 2.5. Question 3, almost everyone got all correct, interestingly. I'm guessing because it was like last year's. And yeah. Yeah. Uh, the mark scheme was you deduct a half mark if you've got one of the scheme ends wrong. Yeah. Yeah. I imagine they would have got the marks. Right. DAX. So DAX, this question again scored abysmally. And it was probably because it was a bit picky. But again, it's just a bit of thinking about how this thing works. So a DAC, I'm trying to convert some binary input to a digital voltage. So what am I trying to create? I'm trying to create something, change something which is 0 dot decimal I minus 1 dot 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 decimal 0. That's my binary number. And I have a voltage range. So this number is between 0 and 1, and my output voltage range is between 0 and Vref, kVref. So how do I scale that? I just scale that by kVref. So that's straightforward. Again, that was straight from the notes. The step size. Simply divide the voltage range by the amount, your entire binary range. Simple enough. The ramp-up converter was this idea that you have a clock cycle and you just keep on ramping up your inputs every clock cycle until you get the correct voltage. So how many clock pulses is it going to take? So it could take 0, it could take 1, it could take 2. Each time you push your binary input up by 1, all the way up to the maximum number. So how many are there? Total, it's 2tn minus 1. Oh, minus 1 there. Sorry? The first one. It'll be in a clock cycle. Oh, well, it depends on. It'll be how it'll connect with the 1 straight away, right? It's just doing a straight compare. Yeah. The successive. I can't say that word. Not with the tooth. So this is the idea, is that you're just kind of going up and down to a range. Again, straight from the notes, just changing a most significant bit, oscillating up and down. And straight from the notes, you can take that to be n. And that's the whole point, is that one is a lot faster. To summarize, question 4 is actually completely straight from the notes. Question 3 is straight from last year's exam paper. Question 1 is a variety, a minor variation of last year's exam paper, and something straight from the notes. And question 2 is half of it is from the notes but asked in a different way. And this bit is just a bit of care to think about what's going on. Have a think about that when the final exam comes around. There will be some bits from the notes, there will be some random questions, and there will be some things that I write which you don't have a chance of solving. Yeah, so really, there's not much I wanted to say, but just trying to give a kick up the backside, make sure that before the final exam you do the full revision and pick up the easy marks. There are, I reckon, 17 easy marks there, and okay, if you want it, definitely get the first 3. You should get 2 of these because, you know, I can allow some room for forgetting. Maybe you should probably pick up the first one because that's quite easy. This one you might have missed. The rest is all from the notes. You should have all that. So, being harsh, that's what I say. It's true. There is a lot of stuff. The first few questions should just be thinking though. What should a DAC do? You're representing a binary number, and you're representing it over an output range. That's just careful thinking. In this, no. In an exam, probably yes. Because, you know, there's only so much time. But, yeah. All right. Okay, back to the lecture. I wanted to just quickly point out about yesterday I talked about priority inversion. I just want to make sure that everyone's aware that there is an example on the web page that you can run for yourself. And what it does, it creates 3 tasks: a high priority task, a medium priority task, and a low priority task. So you have 3 tasks: high priority, medium priority, low priority. Have a look at what each one does. The high priority, it goes to sleep for a second, says it started, prints out waiting on a mutex, so it waits to collect the mutex. Once it has its mutex, it says, I'm very important, I've got to finish my work. Then it posts its mutex and says it's finished. The medium priority, all it does is it runs for a long time. So it has a for loop which does absolutely nothing but consumes clock cycles, and then it finishes. And your low priority says it wakes up first and manages to grab a mutex or a semaphore, goes to sleep for 1 clock tick, and then gives up the semaphore. Now, if you remember, the idea of priority inversion is that what's going to happen is the low priority task is going to wake up first, grab a semaphore, then the high priority task is going to wake up. And it's going to want to run. It's going to start running, and then it's going to hit the semaphore block. It's not going to be able to run because it's waiting on the semaphore by the low priority process. At this point, medium priority comes in and stops the low priority process from running. It carries on, and so the medium priority is running instead of the high priority, which is inverting priority. You can run it yourself, and you can see what happens. I don't know if you can see from your distance, but all three tasks are starting. Low priority grabs a semaphore. High priority tries to grab a semaphore, can't get it, and then the medium priority just keeps on running, consuming clock cycles. And this is the kind of problem that you want to avoid. To avoid that, all you need to do is you can replace, this code replaces all of your semaphores with mutexes. And by doing that, you actually, so yeah, it's just change of name, change of how they're defined, so you have mutex pend instead of sem pend, right? Mutex post instead of sem post. Same idea. You create the mutex, you have to give the mutex a priority, because you're going to want to promote the priority of the process that owns the mutex, so you tell it what priority it should have when it owns the mutex. That's the only extra bit of information, and then you just run it. And if you were to compile that code, you can see that it works. Worth doing that in your own time. But now, the rest of the lecture will hopefully finish off talking about scheduling policies. So, the main thing that we're focusing on an operating system is choosing which tasks to run, or scheduling the tasks. We're going to look at two methods. Rate monotonic scheduling, which is a really simple version, and earliest deadline first, which is also quite simple, but implementing it is a lot harder. The former is a fixed priority schedule. The latter will change the priorities as you run the program. Obviously, changing priorities takes computational effort, so it's costly, but you can actually run, you'll be able to run processes and meet deadlines easier than with a fixed priority. Okay, so we'll talk about some various assumptions we have in our model, and we've actually covered talking about communication. So, how do we evaluate a scheduling policy? If we're talking about a real-time system, the number one thing that we care about is, do we meet our deadlines? If you don't meet your deadlines, then your real-time system is not acceptable, basically. And if you do, then it's great. Having two other important metrics to know is the CPU utilization. We've talked about this a bit. To monitor if you think your real-time system is going to be okay, you probably want to know your CPU utilization. As it approaches 100%, you know you're in danger if you have extra processes, or you could have processes that are missing deadlines when you've got 100% utilization because it's just not making it in time. So we want to monitor that. The other thing we want to model, this is something that you've looked at in labs a bit. So you had to measure the overhead that it takes to schedule, the overhead, choosing which priority process to come in next, the interrupt service routine time. You've monitored all that and measured that in the lab. But if you want to know the full performance of your system, you have to know all these metrics. So, rate monotonic scheduling, it's a widely used, it's a simple policy. This is basically what's done in microCLs2. There's been a lot of analysis called rate monotonic analysis on this, so a lot of mathematicians have sat down, spent a lot of time, and worked out various things, and we're just going to use these results in this lecture. So we have to make a ton of assumptions. So first of all, we're assuming a single CPU for we're trying to work out our worst case execution time, or whether we're going to meet deadlines. gets a lot more complicated when we use multiple cores. It assumes zero context switch time. Now, in practice, context switch time you measured in the labs, it's very small as in comparison to your processing time. Otherwise, you've probably done something wrong. So this is actually a reasonable assumption. But of course, if you're nearing 100% in your predictions, then once you throw in some context switch time, it's not going to hit. We have no data dependencies between processes, so there's no ordering. You have to finish process 1, then you can start process 2. That just makes the analysis much easier. But this is actually quite a big assumption. The execution time is constant, so we have the idea. Well, actually, the next three I'll explain on the diagram. We are thinking of processes that have basically a start time and a finish time. So this is the deadline, and we have a period, and the process can run at any point over this period. How long does the process need over the course of this period to do its computation? It needs a certain amount of computation time, which is modeled by this block here. So note that the computation time that it needs should be less than the period where it can run. Because in practice, what's going to happen is that this block of computation time is going to be broken up into multiple blocks because other processes are going to run in the interim. So this is our simple model. We got a every process has a certain amount of period where it has to complete by, and it takes a certain amount of work within each period. And if you think about all of your tasks which you've written, generally this is the case. You have an infinite while loop. So that would be your period. You're going to have some deadline which you have to meet. And within that while loop, it's going to do a fixed amount of computation. So it's going to use a fixed amount of computation time. Okay. What's important here? So response time, time required to finish the process, or our deadline. The critical instant is a scheduling state that gives the worst case response time, and this occurs when all high priority processes are ready to execute. So you can just think about this. We've got lots of processes at the same time. When is it going to take longest for your low priority process to run? That's when all other higher priority processes are already running or want to run at the same time. Therefore, you have to wait for each one of them to finish all of their work before you can compute yours as the lowest priority process. So yeah, so for the lowest priority process, it has multiple processes, each consuming some of the time, and it has to do its work in the interim. Now each process has a different period. So at the end of this period, process 1 is going to run again. At the end of the period, process 2 is going to run again. And if we just have fixed priorities, then they're going to run the instant they can, down this hierarchy. Much easier to see if you just look at the lot. So yeah, at the end of every period, P1 needs to execute, P2 needs to execute within each period. Now, if you're actually going to schedule it, you know P2 is going to have to fit in this gap. P3 is going to have to fit otherwise. I mean, who thinks this is a schedulable problem? No, shaking heads. It doesn't look schedulable, right? We got P1 occupying basically all of the time with few gaps and a lot of other work to be done. It's not going to be schedulable. Okay, so RMS, what it is, it's a really simple idea, is that the process that has the shortest period gets the highest priority. So it's a simple way. It's not quite how you've done it previously. You've defined which is the highest priority process, saying for the best fixed priority scheme to meet all our deadlines, if we assign it in this fashion, then we're most likely to meet all our deadlines. So yeah, shortest period, give that highest priority. It follows that your priority is inversely proportional to your period. That's just rather obvious. This is kind of interesting, but you can just break ties arbitrarily. You've got two processes that have the exact same period. Then it doesn't matter which priority process runs, but that's actually not that surprising given that we're just thinking about a mathematical model here. And if they take the same amount of time, it doesn't matter which one runs first. Okay, so how does this work? I have a simple example here. P2 has this period, P1 has this period. So which one is my high priority process? P1. So if P1 is the highest priority process, then the second that it's available, which is at the start of every period, it's going to start running. So at the start of the period, P1 runs. Now P2 is also ready at the start of the period, but it can only run once P1 is finished. So it runs shortly after P1 is finished. What happens here? What happens there? Anyone? P1 starts to run here? No. Yeah. This is just, this period here is idle. What happens here? Yeah, P2 has to complete once within this entire period. So P2 is not going to run again. So this is also just idle. So then you'll have your idle process running and counting the clock cycles, which you all know about. Okay, how do we work out the utilization? We sum all of so Ti is the computation time, Tori is the period. So every one of these is going to be a fraction because your computation time is smaller than your period. Sum them all up, and that will be your utilization. Rather straightforward. RMS can meet deadlines with M processes if your utilization is less than M times 2 to the 1 over N minus 1. So this is where the mathematical results come in. They come with their formula, which is as follows. So you can plug in any number of M and work out what your utilization to guarantee that it works. And if you take the limit as M tends to infinity, you're going to get 69%. So if you have less than 69% utilization and you have RMS and you have all the other assumptions, then you guarantee that you're going to meet all deadlines. Okay, so you cannot guarantee 100% CPU utilization. We have idle cycles just to use up the CPU when we're not doing anything else. But we can guarantee we meet our deadlines if our utilization is below 0.69 or 69%. Okay. How do you implement this? Well, you can see it's actually quite easily. You can just have a list of all your processes and a list of all their periods. Once you have a list of all their processes and their periods, then you can assign each of your processes priorities. Once you've got a list of processes and priorities, then you just go through your ready queue and pick the process that has the highest priority. Okay, a simple example. Process 1 has an execution time of 1, period of 4. Process 2, execution time of 2, period of 6. process 3, execution time of 3, period of 12. So first thing we do is we can assign priorities. So which one's the highest priority? P1. This is top priority, then medium priority, then low priority, because it has the smallest period. Okay, then you can work out the least common multiple of the periods. Any idea why you would want to do that? Well, we're trying to schedule all these processes, right? You can imagine that if we work out the least common multiple, then if we schedule over for longer time, it's just going to repeat the process, right? So we can only need to analyze the schedule over the least common multiple. From then on, it's just going to be a repeat of the same schedule with idle cycles to fill up if necessary. And that's how we get a complete or unrolled schedule. Okay, so how would we do this? It's quite a simple idea. Create a simple table with time we can have, and then what we do is we write all our deadlines in first. This is the easiest way to schedule it. So P1 has a period of 4, so it has to finish within 1, 2, 3, 4. So at the end of this point in time, P1 has to finish. Then P1 has to finish 4 later. So you write down all your deadlines. So P1 has to finish every 4 time periods. P2 has a deadline of 6, so we just put in P2 as 6. Put in P2's deadline. P3 has a deadline of 12. Okay, then how do I schedule it? Well, P1 is my highest priority process, so whenever it's available, I run P1. So at time 0, I assume that P1, P2, and P3 are available. If they're all available, which one do I pick? I pick P1. Okay, how long does it take to run P1? It takes 1 time period, so I'm just going to run it for 1 unit at a time. What do I do now? I run P2, P2 takes 2 periods, so I'm going to run P2. And then I'm going to have nothing else to run, so I might as well run P3. Now, you can see that P1 has suddenly become available, so I'm going to run it again. What do I run at this point in time? P2, P3. Hands up for P2. Hands up for P3. Yes, most people say P3. P2 is finished, right? And P2 starts after the deadline. So I have nothing else to run, so I must run P3. At this point in time, now I can run P2. And then I can run P3, and so on and so forth. Right. By the way, an alternate way of doing that is to just fill out, have P1 written in first, write your deadlines first, P1 runs straight away. Then take P2, write your deadlines in, and then say, well, P2 runs whenever it can with the remaining cycles. If you do it this way, then you're less likely to go wrong than if you walk your way through the code. And then you fill in the gaps with P3. Okay? So, just to check that it's utilization. So, utilization is the execution time divided by the period, but we're going to do this over a time span of 12. So P1 runs 3 times in 12, so 3 over 12, 4 over 12, 3 over 12. easy to work out your utilization. You get a total of 10 over 12. So, I told you that if I have 69% utilization, I'm guaranteed to meet all deadlines. But I have 83% utilization. So, am I going to meet all deadlines? No. Who says no? Two people say, no, I'm not going to meet all deadlines with 83% utilization. Does everyone else say yes? Everyone else should say yes, and everyone should say yes, because I just showed you how we can meet all deadlines. So, what is that to say? If we have less than 69%, we can guarantee to meet all deadlines. That doesn't mean that we can't do it with more utilization. And obviously, if you threw in, because we only have 3 processes into this formula, you're actually going to get a number above 69% as well. So it's not that surprising. Okay, earliest deadline first. Same idea, simple idea. It's just we say whichever one needs to complete soonest, we'll get that one right, which is an obvious scheduling policy. You know, this is how we prepare for exams. We go, I got this exam for next, better study for that one, ignore all others. Of course, you're just going to study for this course and get perfect grades, all of you. But yeah, so that's how earliest deadline first works. The problem is that every interrupt, you have to recalculate which is my earliest deadline, because each process is going to have a different deadline. New processes are going to be added to the queue. You have to work out which one is the biggest emergency. And you can imagine that as your processes, if you have 100 processes, computing all of which is the earliest deadline and keeping track of that over time, and every time you add a new process to this list, earliest deadline first would get really expensive, and you'd need dedicated hardware to help you with this. So in practice, you don't often have earliest deadline first, but we'll show how it has various advantages in terms of scheduling. So, earliest deadline first. So I've got P1, which takes this time period. I've got P2, which takes this time period. Okay. How am I going to schedule it? So I've given you the first few things. I say, that's my earliest deadline. Or this is my earliest deadline, so therefore P1 currently has the highest priority. I'm going to run P1. Once P1 finishes, what's my earliest deadline? My earliest deadline is now this one, so then I run P2. Okay, now what's my earliest deadline? This one, so I run P1. Now, what's my earliest deadline? It's this one, so I run P2. Now, what's my earliest deadline? This one. Now, what's my earliest deadline? This one. So, do I run P1 or P2? P1. Does everyone say P1? I say it's not P1. Who agrees with me? So the person who said it should be P1 has agreed with me. He's contradicting himself. Why? So at this point in time here, at this point in time I've just finished running P1, so I've met this deadline. Why would I want to run P1? And why would I want to run P2? Or why would I want to run neither of them? Yes. At this point in time, P2 is finished for this period, and P1 is finished for this period here. Right? So you got nothing to do in this period, so you're actually going to, for this small period, you're going to idle. At this point in time, P2 becomes available, P1 doesn't need to start yet. So until this point in time, I want to run P2. Now what do I want to do? So yeah, now P1 is available and it's the earliest deadline. Therefore, P1 gets run, and now P2 is the next earliest deadline, and it can finish. Okay, so just a bit of care needs to be taken if we're running this example. So EDF can use 100% of the CPU, and it can still miss a deadline. Obviously, if a process is not schedulable, then you can't hit it. You can't schedule it with whatever method you use. If RMS can schedule, EDF can schedule, but the reverse is not true. And this is not surprising because EDF, because it can change priority, it's going to have an advantage in terms of meeting a deadline. Okay, like I said, at every time we're interrupts, you have to choose the process closest to a deadline that's actually available, and in practice it's too difficult to use, or to use in practice. Okay, we have a nice example over this, which I will talk next week.